The MemSat project as a whole is stemming from the idea of putting memristive-based memory into low Earth atmosphere to test it against the background radiation that is seen in space. The main implications of this are that a system in the future, all current electrical systems have to be radiation shielded in order to prevent any upsets or errors from occurring due to background radiation. So the future implications of this project are that potential millions of dollars can be saved on future satellites if this type of memory is resilient to background radiation. That radiation coding does not need to be purchased or even implemented in any future satellites. So this satellite has a huge global impact with not only Rowan as a whole, this is going to be the first satellite built by a New Jersey institution, so it's a pretty big one. We're excited about it. But the main global implications of the satellite are also very important.
So when you're designing a communication system for a satellite, there are a lot of factors that you have to take into consideration. You've got a size budget. You know, a CubeSat is only 10 by 10 by 10 centimeters squared, so that doesn't leave a lot of room for antennas, PCBs, etc. And you also have a power budget because we can only cram so many batteries into our satellite. And we also have to consider the fact that the satellite is going to be roughly 400 kilometers away from Earth. That's a pretty long transmission path. So you have to really make sure that you're going to get your power margins right, calculate your link budget properly, and make sure that you're actually going to be able to talk to your satellite when it's in space.
We have three major organizations that we need to frequency allocate with and meet the standards of. And those three organizations are the FCC, the Federal Communications Commission, the IRU, the International Amateur Radio Union, and the ITU, the International Telecommunications Union. Now, they have there's a lot of intricacies with these three organizations. It's a little bit too complicated for this discussion, but the main things that we're going to point out here are that these three organizations have standards for amateur carrying nano satellites, or satellites in general that want to be using the amateur radio network, which is what we will be doing.
To accomplish our goals with the transceiver system, we had two options. We could either buy an off-the-shelf transceiver, which is fairly expensive, they go for thousands of dollars, or we could design our own. And since we're electrical engineers who know how to design electric hardware, we decided to design our own transceiver, mainly to save money. So here's a prototype of our transceiver. It will allow for us to have full duplex communication up and down to the satellite on two different receive paths, and it should let us broadcast at roughly 32 dBm down to Earth, which is roughly 2 watts of transmission power, which is pretty good for a small satellite. And so this transceiver will act as a slave to the master command module on the satellite, and it will allow us to either send commands from the ground up to the satellite, send firmware updates to the satellite, or report the satellite's health back to Earth.
So our goal and our results here, we've actually completed the base testing. We've completed phase 0 and phase 1, which are the basic idling and connectivity of all the different subsystems. So comms has been a big part of that because the comm system needs to be fully integrated. The next step with that will be actually integrating the transceiver design. Once that has been fully populated and tested, that will need to be done in phase 0, phase 1 testing, and then everything else can be moved on from there. So that's kind of the